MEN stands for multiple earth neutral. It represents a specific configuration of earthing and neutral connections used in electrical distribution and utilization systems. In the MEN system, earthing protective wires are connected together to form a common connection, while the neutrals are also connected together into another common connection. These two common connections are then bonded together, creating what is referred to as the MEN, multiple earth neutral. When dealing with a TT or direct earthing system with elevated earthing resistance, several worrisome consequences can arise in the event of a fault. A high earthing resistance can compromise the efficiency of safeguarding mechanisms like circuit breakers and fuses. For instance, if a fault occurs with a fault current below 10 amps while the protective device is rated at 16 amps, the protective device might not activate as intended. A fault current seeking a path to the earth can lead to a significant surge in voltage across exposed conductive components. This surge can render these parts hazardous when touched, due to the touch and step potential around the earthing rod in relation to the ground. Within an MEN system, the neutral and earth links are interconnected. Consequently, if a fault arises in the frame, the fault current will not only pass through the earth, but will also flow through the neutral conductor via the MEN connection. This setup guarantees a low-resistance pathway back to the transformer, ensuring that the fault current reaches a level adequate to activate the protection device. In a normal scenario, if the MEN link is broken, all household devices will still function as expected. However, in the absence of a functional MEN connection, the setup will resemble a TT or direct earthing configuration. As previously observed, if a fault occurs in any appliance, the resulting fault current directed towards the ground could result in a substantial voltage surge across exposed conductive components. Consequently, the faulty appliance could reach a potential of 230 volts. Yet, the ramifications extend beyond this. All appliances and equipotential devices connected to the earth link, such as stoves, toasters, the exterior of the house, sinks, and taps, will also reach a potential of 230 volts. This circumstance creates an exceptionally perilous environment with the potential for severe electric shock hazards. Let's delve deeper into this by considering subboards that employ protective earth for grounding. In the event of a fault in the main boards leading to an earth connection, all devices linked to the earth terminals will become live. This encompasses the grounding elements within the subboard as well. Now, let's turn our attention to the subboard that utilized an independent MEN earthing arrangement. In the event of a fault to earth, the fault current will also flow through the neutral, resulting in an increased fault current that will subsequently trigger the protective mechanism. Hence, through the implementation of a distinct MEN system outside the main board, the issue of a broken MEN link is prevented from affecting the subboards. The most dangerous scenario arises when the active and neutral connections are swapped. In such a case, the live wire becomes connected to the neutral section of the circuit. Because of the MEN connection, all devices linked to the earth terminal will become live. Despite the apparent normal operation of all appliances, a highly hazardous situation persists due to the electrified earthing link. Let's examine the impact of this on our subboards. When the active wire is connected to the neutral circuit, the neutral link in the main board will become energized at 230 volts. This situation holds true for the neutral links in distribution boards 1, 2, and 3 as well. Owing to the presence of MEN connections in the main switchboard, distribution board 1, and distribution board 2, all the earth links will also become energized to 230 volts. In the case of distribution board 3, as the protective earth is powered through the MEN of the main distribution boards, the earth link will likewise be energized to 230 volts. This presents an extremely hazardous scenario that you certainly want to avoid within your switchboard, as this state will endure as soon as power is supplied to the switchboard. In this situation, we examine the impact of an open circuit in the neutral line. This phenomenon can occasionally take place in overhead power lines, where the cables are frequently swaying due to the wind. The neutral conductor might become dislodged or fractured as a result. The presence of an open circuit neutral in an electrical installation can pose significant dangers and consequences. The neutral wire serves a crucial role in electrical systems, providing a return path for the current to flow back to the source. When this neutral connection is disrupted or severed, a range of hazardous situations can arise. When there's an open circuit neutral in an electrical system, the normal return path for current is disrupted. Consequently, electric current flows through the grounding system, returning to the transformer. In this scenario, the combined resistance of the earth and the load creates a voltage divider effect. As a result, the voltage between the earth connection and the ground fluctuates based on the load's conditions. Let's analyze how this situation affects our subboards. If there's an open circuit in the neutral at the main switchboard, you'll observe that the current won't be able to travel back to the transformer through the neutral from any of the distribution boards. Each neutral return from the individual distribution boards will pass back through their respective MENs. As previously explained, when the load is raised, all the components linked to the earth bar will become energized.